everybody, thanks for coming. It is my pleasure to introduce my friend and former co-worker Mark Thomas. We met in 2011 when we both joined Microsoft Research as postdoctoral researchers. I decided in 2013 that I would rather find my luck elsewhere. Mark stayed a little longer until a couple of months ago when he joined Dolby. He has worked on many topics. Like his PhD was on glottal synchronous speech processing, right? Then we did a lot of spatial audio, especially at Microsoft, like HoloLens and all that. Kinect, all this kind of products. And this time he's speaking about dereverberation, channel equalization. Due to the fact that he's done a lot of productization, there are certain legal restrictions as to what he can talk about, but this is a public topic, so please enjoy.
Thank you, Jens. Yeah, so thank you for your very kind introduction. As you alluded to, I've been doing quite a lot of work with spatial audio capture and reproduction over the past 4 or 5 years, and this is a little problem that just seems to keep coming back like an itch that you can't scratch. That I do a little bit of work on the dereverberation problem, and then think I've sort of done that for a while, and then a year later it comes back. And I think one of the reasons why I find it so interesting and somewhat elusive is that the problem of dereverberation when it's channel-based is that we assume that we have some knowledge of the acoustic channel between a talker and a microphone or a microphone delay. And it feels like you've got a lot of information there, and you should somehow be able to use that information to get rid of the reverberation, and it turns out to be an awful lot harder than you might originally think. So the scenario is one, and this is actually applicable to lots of different scenarios, but one when you have a talker and there's some impulse response between that talker and a microphone array. So we've got something here like a Microsoft round table device. Sorry, did I say Microsoft round table device? I meant to say Dolby conference phone.
Yeah. I got it.
Anyway, so the phone is going to be picking up the wanted talker. The wanted talker is the thing that we want to keep. There is also going to be noise which is not co-located with the talker, and that's often a useful thing to know because if we have a microphone array, then we can make use of that microphone array to point a beam towards the wanted talker using beamforming. Also, noise tends to be somewhat uncorrelated and independent of the talker, so we've got noise suppressors. And there are tools that we've got that you'd find in any textbook on speech capture that you can use to get rid of noise to some extent. There's also the problem of acoustic echo. So the device has got a loudspeaker right next to a microphone, and that microphone will inevitably pick up what the loudspeaker is playing after having been filtered around the room. And if you don't have any kind of acoustic echo control, then the person at the other end is going to start hearing their voice coming back at them. This is a kind of supervised problem in that we know the sound that's coming out of the loudspeaker, we know the sound that is being received by the microphone, we can attempt to estimate the transfer function and then subtract that. So this is, it's a convoluted process, but we have a supervised element to it, so we can actually subtract rather than deconvolve. The problem area is that of reverberation. Now this is a blind problem. You don't know the source signal, the talker. If you were to know this, then none of this would be an issue. And the sound gets bounced around the room, and what you end up with is a mangled version of the talker. And although we have tools for noise suppression, we have tools for echo cancellation, there's no sort of be-all and end-all tool that you would find in a textbook that says this is the way you do dereverberation. Admittedly, some dereverberation happens when you do beamforming, and some of it happens when you do some noise suppression, but there's not really anything that you would say this is the dereverberation tool. So, in this talk, I'm going to be looking at the problem of dereverberation when we have an acoustic channel, and looking at some of the issues that arise. We'll derive some elements of the MINT algorithm, which is a fairly well-known method for doing multi-channel dereverberation. Unfortunately, it turns out that this is not very robust, and so people have spent a lot of time trying to do robustness enhancement by doing things like channel shortening, and there are other tools that can be used, like regularization and such. These, unfortunately, are also limited. So what I want to talk about is this new approach where we try to jointly do beamforming and channel equalization. And the rationale behind this is that beamforming is known to be a very robust and very well understood technique, but it's never going to give you perfect dereverberation. Channel equalization does have the potential to do perfect or near perfect equalization, but it's extremely brittle. And if you have any kind of mismatch between the expected system and the actual system, or any additive noise, then this can cause the whole thing to blow up. And what can sometimes happen is you end up having more reverberation at the output of the output and less. And then, conclusions. So I'm going to jump straight into the problem. So let's assume that we have knowledge of the reverberant impulse response between a talker and a microphone. And we'll just assume that we know this exactly at the moment. And our aim is to find an equalizer, which we'll call G of n, so both of these are in the time domain, such that the convolution between H of n, the channel, G of n, the equalizer, is going to be a delayed unit impulse function. So what we're saying is that, with the exception of some latency that we've introduced by this element tau, that we have completely removed all the reverberation. We've flattened the magnitude response, we've linearized the phase response, and we've got no reverberation left. Now, on the face of it, it looks like this is very easy. Compared with the kind of case where you just have a beamformer or a noise suppressor, which don't really know very much about the environment, we're assuming that we know everything that we need to know within this H of n. And we've got a fixed system, we're going to assume that this doesn't change over time. It's semi-supervised in the sense that we know this channel already, even if we don't know the source signal. And as will be shown later, there's also a closed form solution, so we can actually get to the answer very quickly. So let's start off with a very simple toy example. So let's pretend that the impulse response is an anechoic one, and it's just a single unit impulse at time 0. And our target, which we're calling E of n, is just a delayed unit impulse. So therefore, in this case, the equalizer, if you can even call it an equalizer, would just be a delayed delta function. So let's just introduce one more non-zero tap. Again, our target is an impulse at 10 samples, but now we've got a sample at tap 1 and tap 3. Can anyone guess what the equalizer might look like? Yes?
Very complicated.
Very complicated.
Long and complicated.
Very long and complicated, yeah. It's perhaps to some it's a surprising result. Here's an example of what such an equalizer might look like. And what we can see is on the right-hand side, we're not actually getting perfect dereverberation at all. We've got these wobbles. So this is just a least squares solution to the problem. There's no complete inverse. We'll look later as to how we actually form this optimization problem, but for now I just want to stay high level and get some intuition. Now, one thing we notice is that the forward system is just 3 taps long. The inverse system that I've got here is 512 taps long. I could make this infinitely long and I still won't get to the true inverse.
It's just a Z-transform, right? So you just invert the Z-transform and get the exact impulse response?
Well, let's have a look at the next thing. So the Z-transform would be... Thank you for anticipating that. So yeah, there are several different ways of looking at it, and one of it is in the time domain that tells us something about where the taps are, but it doesn't tell us anything about how hard it is to invert it. So the one way of looking at it is spectrally. So if I've got a tap and a delayed tap, then this is giving me a cone filter, which you might have if you happen to be talking very close to a reflective surface. If you talk next to a wall, then you get this cone filtering effect. It's also used to artistic effects in tape delay and flanges. And the thing that characterizes it is that when you've got a delayed impulse like this, then you end up with a Fourier transform that's a sinusoid, and then when you take the magnitude of that, you end up with something that's got regular dips. And it just so happens that in this case we only have one dip before we hit the Nyquist frequency, but the number of dips is related to the time delay between those two impulses. So what it's saying here is that we have absolutely no information at a certain frequency, so we're never going to be able to recover it. It's been removed completely. Another way of looking at it is, as Malcolm pointed out, is that you take the Z-transform. So you treat it as a Z-transform, you factorize it. So we've got 16 taps here, most of which are 0. You're going to end up with 15 factors, 13 of which are just going to end up at the origin that don't really do anything, but 2 of them are going to end up on the unit circle. They just so happen to be lying on the imaginary axis. So if we know where the zeros are, we should just be able to cancel this with a filter that's got poles in the same place. But if we're going to put poles on the unit circle, we're going to end up with an oscillator. An oscillator doesn't end, it goes on forever. So we already know that we're going to have an infinitely long equalizer, but things get a little bit worse when we start introducing more taps. So I've added in 2 more non-zero taps here. And if we look at this in the magnitude spectrum, we see that it no longer goes down to 0. So this, on the face of it, looks like a good thing. But if we then factorize the C transform and plot where the zeros are, 2 of these happen to have fallen outside the unit circle. So not only do we have a system that involves an infinitely long inverse, the inverse also happens to be unstable, because poles outside the unit circle will end up blowing up. So clearly this isn't the right way to go. We're going to hit a problem if we're trying to do single channel dereverberation. So let's start building up a list of requirements. First one is we're going to need more than one microphone. And not only do we need more than one microphone, but we also need to be sure that the impulse responses contained between the source and each of the microphones do not contain common zeros. So these zeros can't lie in the same position. Now this is something that's been debated quite a lot in the literature, and it's not fully agreed on as to what counts as a common zero, how close to 2 zeros have to be until we say that they're common. But for the purposes of this talk, I'm going to assume that there are no common zeros and that each channel doesn't overlap any other one in the complex plane. So let's add a new microphone. So on the top left-hand corner, we now have the system H1, which has got impulses in the same position as we had in the earlier example. But now I've got another system that's got 2 more impulses that happen to be a little bit further apart and slightly delayed. So this might happen if you have a microphone array. One of the microphones might be further away than the other one. It might be sensitive to a different reflection. And this is a very simple toy example. But if we then calculate the inverse filters here, we end up with a system that involves H1 convolved with G1, which is not an inverse, and H2 convolved with G2, which is also not an inverse, but the sum of the output of these two is an inverse. And it turns out that this is an exact, there's a unique and an exact solution to this. And again, I'll look at the optimization problem in a few slides' time. But one nice property of this is that now we have a filter in our inverse transform that's an inverse filter that's much shorter. It's not going on for infinite time. Here it's bounded. I happen to have set it to be 16 samples, but I can make it even shorter than that. And if you treat this as an information theoretic problem, you can derive an inequality that says that the length of our inverse filter, Li, has got to be greater than or equal to the ceiling of the ratio between the length of the forward filter, the impulse response, and the number of microphones. So what this is saying is that as we add more and more microphones into the system, we can have inverse filters that get progressively shorter. We can end up with inverse filters that are shorter than the filters that might exist in our forward filter, which is a bit surprising result. So this is all looking kind of good so far. So let's add one more thing to our list of requirements. This is the inequality. So let's look at what happens when we've designed the system and now we add a little bit of perturbation. So what I'm going to do is look at the first, the second non-zero impulse in the first system, and I'm just going to move that along by just one sample, so it's a very, very small change. If I do that, then what now happens is the whole thing blows up. We then get this chaotic behavior in the resulting equalized response. So just by moving one tap, that's enough to create a bad response. So what we can say from this is that it's not a very robust solution. We need to do more than this. One phrase that keeps coming to mind is by my former supervisor, Patrick Naylor, that the inverse of the estimate is not a good estimate of the inverse. And this is certainly true in this case. So those were toy examples where we've only got a handful of non-zero taps. What if we've got something like a room impulse response, which could potentially have thousands of taps, and we could have potentially millions of reflections in there? We've got a very, very complicated system, and trying to invert it in this way and making the assumption that it's not going to change, that's not really very feasible. Impulse responses will always change over the time. We've got movements in the source position, we've got movements in the position of the microphone array, just the movement of furniture around the room or the change of the temperature in the room. This is enough to make enough of a difference in the acoustic impulse response to make this inverse not be very robust. So sadly, we're going to have to add one more thing to our list of requirements, and that's that the impulse responses need to be known exactly. This, of course, isn't feasible in the real world. Now, this set of requirements is part of what's derived in what's called the MINT algorithm. This is the multi-channel or Multi Input-Output Inverse Theorem. And there are many different variations of the MINT algorithm in the literature that try to improve the robustness. And a lot of them do this by trying to relax the constraint that we want a perfect impulse at our output. We want to make it something a bit wider than that, so we have a bit more degrees of freedom, and maybe let's not try to do complete dereverberation, but try to get something that somewhat approximates it. I can put this as a formal statement. We can drive this as a linearly squared problem. And what we're saying is that we have some filtering matrix H. I'll show you what that filtering matrix looks like. That when filtered with G, which are the inverse filters that we're trying to derive, and subtracted from the desired response, which is just going to be the unit impulse, we want to come up with some kind of system that minimizes this equation. The filtering matrix H is actually built up of lots of smaller filtering matrices. So what I've done is I've taken filtering matrices and stacked them across the horizontal axis. Each of the filtering matrices is just a shifted set of the original impulse response. So I've taken the filter H, the channel is M, and I just have to make the second subscript the tap index. And this is a convolution. This is the same thing that you get if you did conv MTX in MATLAB. Similarly, we've stacked the filters G that we're trying to design. So these are column vectors that have been stacked together into one big long column vector. And then we can very easily find the solution to this just by taking the pseudo-inverse of this matrix. So at least we can get a solution in a closed form way, and we can at least do this very quickly. There's no need to do a kind of adaptive solution. We can put this into a more general framework, whereby we can just extend this to any number of channels. So on the left-hand side is all the stuff that I can't control. We've got a speech signal, which we'll call S of n. This gets filtered by this set of filters H, which are the impulse responses between the source and each of the microphones in turn. This produces reverberant signals X, which we can't observe directly because of the effect of additive noise in the form of B. Y are the things that we can observe. So Y are the signals that end up being seen by the microphones. And our aim is to derive this set of equalization filters such that when we filter each channel by each filter and then sum their output, we then get an estimate of the speech signal. And all the way through this talk, I'm going to be generally thinking more in terms of vectors, just because they tend to be a bit neater to put down on paper. So we've seen how MINT is not very robust. We can make it more robust with one technique called channel shortening. So if we look at an acoustic impulse response, we can split it up into different parts. We can say that there's going to be a direct path, which is just the anechoic impulse response between the source and the microphone. Then we've got early reflections caused by hard reflections like the walls and tables and that kind of thing. And these reflections become reflections of reflections, and eventually you get a very high density of reflections whereby you can't pick out any reflection in turn, but instead you get this decaying distribution, and there's an exponential here. And when people talk about decay times or reverberation times or T60, they're talking about the rate of decay, this exponent. So what we can do is split it into early reflections and late reflections. And some of the literature suggests that the early reflections tend not to be perceived as reverberation. They're instead perceived as a coloration. Certainly in Cuttress's book, and there are several papers that have come since, that suggests that anything less than about 50 milliseconds will make it sound coloured, but that doesn't really affect the intelligibility in the same kind of way as the reverberation tail does. So a reasonable thing to do is to say, well, why don't we relax the constraint? We say, well, let's not try to give us an exact impulse, but let's just say, give me something that's maybe 50 milliseconds long, something that doesn't sound like reverb, but might be a little bit coloured, and that might be enough to give us a dereverberation that's a bit more robust. And this kind of approach, channel shortening, was conceived in the communications literature for mitigating inter-symbol interference. So if you've got a transmission line and you happen to have a packet that ends up getting dispersed, that dispersion can be thought of as a kind of reverb. The support gets wider, and these symbols would tend to start overlapping. And the idea of channel shortening was just to try to prevent that overlap. Let's not try to get back to the original signal, but just at least shorten it enough so that we no longer have an overlap between symbols. So one of the algorithms I'm going to look at is the robust multi-channel least squares, or RMCLS algorithm. It was conceived by Wangcheng Zhang, who was a PhD student who was a couple of years behind me at Imperial College. And all it does is it takes the mint problem and adds in this extra weighting function. And this weight happens to be a matrix, it's a diagonal matrix, and the entries of that matrix are pretty simple. They're all ones for the duration of our time delay tau. After that we have what we're calling a relaxation window, during which we say let's not constrain our taps at all, let's let those taps take whatever value they like, and this might be 50 milliseconds or some other value, and then after that point we say let's try to suppress it. So it's saying let's suppress down the tail, but let's not suppress anything else. So it's natural to ask how we choose this window length. 50 milliseconds might not be the best one. One way of looking at it, actually there's one other thing, there's a closed form inverse to this. One way of looking at it is to think about the amount of energy that might get put into a system by these filters. So these filters have a norm, and if that norm is big, then it means that if there's any mismatch between G and H, then we'll end up with bigger errors. And if we plot as a function of relaxation window time the gain that's put in by this filter, so the filter norm, we see that it reduces. And this was just done with some simulations. Using the source image method, I simulated a room of 5 by 4 by 4 meters, at a 260 or 300 milliseconds. And so what we see is that this gain goes down. So if we have no relaxation, then we're effectively the mint algorithm. And we see here that the gain is in the order of 50 dB in this case, and 50 dB in anything to do with acoustics makes me shudder. This is definitely a big amount of gain, and we'll have to try to get away from that. Fortunately, as we increase the relaxation window length, then the gain starts to go down, and there's quite a lot of literature out there that shows that if we reduce the gain, then this will eventually give us a more robust solution. So I got really excited at this point. Up until the point that I'd been learning about dereverberation, I'd been doing characterizations of rooms and thinking about the dereverberation problem, but not in any kind of formal way. And then when I came across this, I thought, this is great, I can start doing real dereverberation. Yes, ma'am?
So is there so much energy in the first couple of milliseconds? Because nothing in your room would reflect that fast.
So, okay, so this isn't the energy in the first couple of milliseconds. It's saying that if I design a filter that doesn't have any relaxation, then this is the norm of that filter. If I increase the relaxation window, then the norm of that filter tends to go down. It's not trying to do such a stringent thing. It's not trying to get me to a perfect impulse, but it's got all this extra freedom because it can make those early taps whatever value it likes, and that has the effect of reducing the norm of the filter.
Yeah.
Yes, yes.
And I mean, the gain still stays at more than 20 decibels.
It's still pretty big, isn't it?
Even for like after dozens of milliseconds. And 20 decibels, that's a factor of 100.
Yeah, it's a lot.
10. 100 or 10.
Well, it's a lot. 20 dB would be 10 times.
Yeah.
Yeah, it's still a lot of gain. And
so if there's noise or something on the microphones then.
Yeah, and we'll see this in a few slides' time. So yes, it certainly makes it more robust, but it needs to go an awful lot further. But I got excited. I thought, well, we've got an algorithm here that might be able to do some dereverberation. So I went out and measured a real room, so a room of 5 by 3 by 3 meters. T60 was 170 milliseconds, so it was like a reasonable conference room. And I did a supervised estimation of the impulse response between a loudspeaker and 2 microphones. So I had a good estimate of the acoustic impulse response. And immediately after that, I played back some speech through the same loudspeaker. So I didn't move any furniture, it was almost at exactly the same time. So this is presenting pretty much the most ideal real-world scenario that I could ever get. And then using an objective quality measure of PESC. So PESC is an objective measure of speech quality that was originally designed for estimating the subjective score that you would get if you were listening to coded speech. But there is some literature out there that suggests that it's also a fairly good estimator of how reverberation sounds. So I've used PESC, and certainly when you listen to this out loud, then you can certainly hear the differences in the amount of reverberation, but in a room like this, it's pointless playing back anything because they all end up sounding the same. But if I do unprocessed speech, so in other words, I just take the raw microphone signal and run PESC through it, then I get PESC of 2.6. PESC is on the scale of 1 to 4.5. It never gets more than 4.5. And I think 2.6 is in the region of what is deemed to be bad and annoying. If I then apply meat, so in other words, I RMCLS with no relaxation window, I get PESC of 2.2. So the PESC has actually gone down, so the algorithm has actually made it worse. And as you listen to it, then subjectively it sounds like there's more reverb than you originally had, so it's done more harm than good. Then as you start introducing relaxation to 6.25 milliseconds and then to 12.5 milliseconds, we start getting better PESC. And so it's showing that we're at least getting some improvement. But we're seeing half a PESC point in the absolute ideal condition, and this worries me a little bit.
So is that mostly because of the room isn't stable, or the measurements aren't stable?
Well, natural question is, yeah, why wasn't it the same? And so I probed around a little bit later with some more experiments, which I'll come to in the next slide. So before I do that, I want to introduce the idea of projection misalignment, which is really just a measure of the distance between one impulse response and another impulse response. Its derivation isn't so important, but it's just a measure that's often used in the literature. And so I wanted to probe around and see, was the problem because I had a mismatch between the channels, or was it because I had noise? And so what I did was ran a set of simulations, the same conditions as I did a few slides back. So I've got this 5x4 4x4 meter room, with 2 microphones in it, a system of 1024 samples and an inverse of 1023, T6300 milliseconds. What I then did was see how it behaves when I only have noise, and how it behaves when I only have channel error. So in the case when I only have noise, that's this. If I have an infinite SNR, so in other words I have no noise at all, then I get this purple line here. And not surprisingly, when I have no relaxation window at all, Mint gives me the perfect score of 4.5. I've got perfect dereverberation.
What's the vertical axis?
So the vertical axis is the PESC score.
Okay.
So the predicted mean opinion score with PESC.
Okay.
And then as I introduce a relaxation window, then because I'm starting to introduce this spectral distortion that comes in by having this non-unit impulse response, I then get a slightly worse PESC. Then the second case is when I have 40 dB SNR, which is still pretty low noise level. What we find is now there's an empirical optimum that lies sort of somewhere around 15 milliseconds or so. Then when I start going to 30 dB and lower, I start approaching these dash lines, and these dash lines are what happens when I do no processing at all. So that's just the microphone 1 signal. And so what I see is that by the time that I get lower than 30 dB SNR, then I'm no better off doing any processing than not doing any processing. So even when I've got the luxury of doing this relaxation window, that's not enough. So clearly noise is a factor here. And then when you do channel error only, so now I have no noise, but I introduce channel error in the form of this projection misalignment. So I'm adding errors deliberately to achieve a certain NPM. I see that when I've got no channel error, then I get my PESC of 4.5. When I've got no relaxation, then as I increase the window, the result goes down. And again, there's an empirical optimum. If I introduce these errors, then the empirical optimum starts going up. But again, if I introduce enough channel error, then I end up being close to this dash line, and I'm doing no better than if I did nothing. It's a bit hard to get a feel for what these NPM values mean, so a little bit later on I'll look at what NPM you get when you start perturbing the source. So rather than adding errors in that way, instead I make a spatial error when I move the source around. But just take note that when I get to about 10 dB, minus 10 dB, then I don't get any kind of improvement. So that 10 dB is worth remembering. So we're getting a little bit closer, but to be honest, I'm not convinced. We can get marginal improvements under ideal conditions, but it's not nearly as good as it could be. And it makes sense that when we reduce this filter norm, that we get a slightly more robust solution. This is something that's in the literature, and it kind of makes sense. And maybe I'm being a little bit harsh. There's a lot of literature that looks at not just channel shortening, but instead the reshaping of impulse responses and the adding of regularization to try to make it more robust and less sensitive. So there's a lot of good literature out there. So it doesn't mean that this isn't worth probing, it just means that certainly as far as this RMCLS algorithm is concerned, it has limitations. So this brings me on to the new approach, which involves joint beamforming and channel equalization. So let's go back to the framework of a channel equalizer. So on the left-hand side is the stuff that we can't control, and on the right-hand side is the stuff, these Gs that we are aiming to design. So this is what a channel equalizer looks like. This is what a beamformer looks like. If you didn't notice the difference, there is none. They're actually identical. So they're both optimal in their own senses, they just have very different optimization criteria. So what we want to do is perhaps leverage the known robustness of a beamformer with the potential dereverberation performance that you get from channel equalization. So on a very high level, all a beamformer is doing is a spatial sampling. So you've got microphones at some point in space, we're sampling that space, and a beamformer is applying a model that says that if a source is coming from a particular direction, then this is going to produce a certain set of interchannel delays. And if we know what those interchannel delays are, then we can exploit that fact and then create a beam that points in the direction of the wanted talker while suppressing energy that arrives from a different direction. And again, we have these observations Y, we put them through these filters G, sum them together, and then get this filter in some beamformer. So let's make some comparisons. Beamforming is very well understood. The idea of robustness of beamformers has been very well studied in the literature about communications, and it's come over to the world of acoustics and audio. So we know a lot about robustness and how to make them robust. We also know a lot about how to design microphone arrays that give us good beamforming results. So for instance, if we have two microphones, we can get a tighter beam and more echo suppression and more noise suppression if we have them in an end-fire configuration than if we have them in a broadside configuration. So there are lots of nice criteria that help us design microphone arrays. There's also relatively little training required. So with the channel equalization case, we assume that we already know something about the acoustic impulse response, which is quite a lot of information. With the beamformer, we might want to know the geometry of the array, we might want to know something about the characteristics of the microphones, but we don't need to know anything in more detail than that, usually. The drawback is that they can never produce perfect dereverberation, and this is due to the fact that there are several common assumptions made. One of them is that microphones are often assumed to be omnidirectional. This isn't always the case, but microphones tend not to be omnidirectional, so there's a mismatch between the model and what happens in the real world. So in other words, microphones become more directional at high frequencies, whether you like it or not. Often there's this assumption of plane wave incidence. Again, this isn't always the case, but often it's assumed that a beam is a function of angle, it's not a function of range. So we assume that the plane waves are coming from a long way away. But the real reason why they're limited is because there's often this assumption of anechoic propagation. So even when you have an adaptive beamformer that is somehow adapting to real-world conditions that tries to, for instance, point a null towards a noise source, it still has to have this notion of distortionless behavior. And the definition of distortionless is if a source happens to be arriving from this angle under anechoic conditions, then we have a unity transfer function at the output of the beamformer. Now, channel equalization is different. It has the potential to achieve perfect or near perfect dereverberation, and it does this by exploiting knowledge of the entire room. It doesn't just know about angles of arrival, but it knows a lot about the reverberation in the actual room that it's placed in. The disadvantage is that we need to know this information in the first place. It may not be reasonable to know the reverberant impulse response for a source at every single point in space, and we'll look at this point later on. And as we've already seen, they're extremely sensitive to noise and estimation error.
So could you also say that the optimization is all the same, but the beamforming has a very restricted set of solutions because it assumes it has to be a plane wave, and I think we said that, but
yeah,
it feels like it's the same thing except for the constraints.
There are two differences, and it needn't necessarily be a plane wave assumption, but that's often the case. The big difference is that, again I'll come into this in a few slides' time, is that with a channel equalizer, we assume we have impulse responses between a fixed array and a point and a source at one point in space, and that's all we know. So we know reverberant channels, but the source is only in one position. A beamformer relies on knowing the response as the source moves to many different places, and usually, like in the case of an NVDR type beamformer, we'll say, let's try to suppress energy from all directions under the constraint that anything coming from a particular wanted direction is undistorted. So the channel equalizer knows a lot about impulse responses in one direction. The beamformer knows less about the impulse responses, but it knows it in lots of different directions. And that's where a lot of the robustness comes from. And I'll give some examples of how we can join those two together in a minute. But before I do that, I want to introduce some additional notation. So we are familiar with these vectors, H, so H is our impulse response and M is our channel index. I want to put this little V symbol over the top, and this is meant to depict a reflection. So if you've got a V over the top, then this means I've got a fully reverberant impulse response that looks long like this. If you've got a little arrow kind of means direct path only, so this is an impulse response that's anechoic. This doesn't necessarily mean that there's only one non-zero tap, because there may be non-integer delays, in which case it spreads out in something like a sampled sinc function. But when we see the V, we mean fully reverberant. When we see the arrow, then we mean anechoic. And then the X, as I'll describe in the next slide, is to do with a position in space. So if we're going to design a practical beamformer, then often we want to know its response in several different positions in space. Now here I happen to have put it in a circle. You could put this on a sphere, or you could sample it at several different points, but just for the simplicity, we've got it on a circle. So we've turned this into p different points. We've split it up. The x underscore p is the pth position. P0 is what I denote as the look direction. So P0 is what occurs here. So let's look at mint in this new notation. So it looks almost the same. The only difference now is that the convolution matrix has now got its V over the top to show that it's fully reverberant, and it only knows about the impulse responses in the look direction, doesn't know anything else. Recall that the H has been stacked horizontally over M indices, so that all of the M microphones have been stacked in a horizontal direction. If we look at the filtering sun beamformer, it's not so different. And this has all been derived in the time domain. Typically this would be done in the frequency domain, but I want to have some degree of compatibility, so everything is in the time domain. So now we've got a minimization problem where the optimization criterion is derived on the anechoic impulse responses. So it's saying, give me as close a match as you can to the desired response, and the desired response here is a bit bigger. And I'll show you what I mean by that. So H, in the previous case, had been stacked over all microphones in the horizontal direction. Now we stack over P positions in the vertical direction, so we have a much bigger convolution matrix. So G stays the same size, but the H gets a bit longer. Similarly, we now stack the desired response over P positions. We've got a very long desired response. So in the look direction, it remains this delayed impulse. For all other directions, I'm just saying that this has got to be 0. So in other words, I want a 0 response in every single point in space, with the exception of the delayed impulse, which I get in my look direction. And to make sure that we get this additional constraint, we have now this subject to the constraint that when we have a source in the look direction, that we get exactly the desired response. So this minimization criterion will get squashed down as much as it can be, but this equality ensures that in the look direction we always get an exact response in the desired direction. So now that these have been derived in a similar kind of framework, we can ask the question, well, can we bring them together, and can we get the spatial robustness of beamforming with the dereverberation performance of channel equalization? So we can assume that we have an oracle solution. This may not be very practical, but let's assume that we have probed the space in many different directions. So we now know there are fully reverberant impulse responses for a source at many different points in the room. So it's much like the beamformer, except now we're working with fully reverberant impulse responses. We end up with an optimization framework that looks almost exactly the same. The only difference is that we've now replaced the anechoic convolution matrices with fully reverberant ones. So I say oracle in the sense that we have probed the space in lots of different places. Now, realistically, we can't really do this. So if you had something like a conference room scenario, you would end up setting up a microphone array and then moving a calibration loudspeaker to lots of different points in space, and that's just not really a very practical thing to be doing. So what you could then do is some kind of hybrid case. fact, before I move on to this, I should just point out that this constraint is actually the mint cost function. It's exactly the same. And also that I've added this relaxation. So rather than trying to get an equality and say that we need to have an exact dereverberation in the loop direction, instead I say let's get it a little bit closer by putting this inequality, and this is a parameter that we can tune later on. So back to the idea of having a hybrid solution. So this is, again, almost exactly the same as the optimization criterion before for the Oracle case. Here we derive the response to sources that aren't in the loop direction purely from the array geometry. In other words, we assume anechoic conditions for those source positions that don't lie in the loop direction. And so if you were to make a practical system, you might just have a calibration null speaker that you would put somewhere near where you would expect a talker to be, and that would be it. You would just measure the reverberant impulse responses in one direction only, and then for all other positions, you derive this filtering matrix just from the geometry. And so that's getting to something that might be a little bit more practical for a real-world scenario. So I ran some simulations, and here I made a 5 by 5 by 5 meter room, and I placed a 3-element linear array in an N5 configuration just off the centre of that room. Again, we used the source image method to simulate it. The inter-microphone spacing was 1 centimetre, which was pretty tight. So what we're looking at here is a snapshot of what happens when we move the source away from its intended position. So this is showing the normalized projection misalignment. So it's giving us an idea of the distance between the source in its intended position and the impulse responses that arise from when you move that source to a different location. So we're not seeing the whole room here, we're just seeing a small snapshot bit here. And what we see is that when the source is in the intended position, then we get no error. And then as soon as it moves away, then we start getting errors introduced by the fact that there's now a mismatch between the intended system and the system that you get when you move the source.
Sorry, just to make sure I understand it should be 1.2, 1.4, 2.4 there.
I'm sorry?
The X labels.
The X labels, that's 1.4 meters. Yeah, so this isn't the entire room.
Oh, but you said it was centered at 2.4, I thought.
Okay, the microphone array is in the center at one point, so it's a meter away. This is the source. So yeah, I should have zoomed this out a little bit. You can imagine where the array might lie. You see this curved here. This is actually the locus of position. So the direct path has got a constant delay. So it's the biggest tap. So that the microphone array is somewhere down here. But if we look at the numbers, we see that for the majority of cases, we've got worse than minus 10 dB. And this, we saw with those simulations previously that if we've got anything worse than 10 dB of channel misalignment, then it's hopeless trying to do any kind of channel shortening. And really, it just takes a few centimeters to make an error like that. So it really is a much harder problem than I initially thought. I assumed that 10 dB was a lot, but actually it turns out 10 dB is not a lot at all. Just a few centimeters will get you a lot worse than that. And so this predicts poor mint performance. Another thing I just want to introduce now is the idea of white noise gain. So previously we were looking at the filter norm as a measure of robustness. What you can do is think of the amount of gain that gets put into the system for an individual frequency. And this is a technique that's used an awful lot in beamforming. And white noise gain then tells us how robust it is to sensor noise. So if we have a lot of white noise gain and we add some uncorrelated white noise within the sensors, then we're going to start boosting that noise. Ideally, we would like to constrain that white noise gain so that we don't boost the sensor noise too much. So here, these H's are almost exactly the same. You don't see my... I've been assuming you've seen my mouse, and no, you don't see my mouse. The underline H just means that we're in the frequency domain. So let's look at what the white noise gain does. So I set up that scenario and solved the solution, got the solution for mint, for the filtering sun beamformer, for the hybrid solution, and the Oracle solution. And this is the white noise gain that results. We've got frequency along the x-axis, and then on the y-axis is the white noise gain. The blue line is a pretty classic curve. This is the kind of thing that you would see in a textbook on beamforming. What we see is that the white noise gain gets worse at low frequencies. An intuitive way of thinking about that is that if you have a wavefront impinging on a pair of microphones, a beamformer will be exploiting the pressure gradient between those two microphones. And if we've got a very long wavelength, then the difference in signal gets smaller, and that's the reason why we end up having this extra white noise gain. So this is an expected curve. What wasn't expected, at least not for me, was that the filter and sum beamformer is actually adding the most white noise gain. The mid solution is adding the least. So in some guys, you might expect that mid would be the most robust, and we basically know this isn't true. So white noise gain as a measure of sensitivity to uncorrelated self-noise is not necessarily a good predictor of how spatially robust the signal is, the system is. Then somewhere in the middle we've got the hybrid and Oracle solutions, and I was a little bit surprised to see how similar these are. That the Oracle solution knows an awful lot more information than the hybrid solution, but we end up with what seems to be a fairly similar result, at least as far as the white noise gain is concerned. So what I'm doing now is plotting a map just in the same kind of way that we did with the NPM. So I'm looking at the resulting PESC score that you get when you move a source away from its intended position. So this gives us an idea of how well it performs with spatial error. So MINT gives us a peak at 4.5 when the source is exactly the position it should be. And then as it moves slightly out, then it does a lot worse. And the shape of this is the same as the shape of that NPM plot. So NPM is a good predictor as to how well MINT is going to perform. Now the filter and sum beamformer doesn't look like it's doing a whole lot. This is again partially because we're too far zoomed in. If we were to zoom out, then we would see that we're actually in the main lobe of the beamformer. And so although we don't get a nice tight peak occurring in the filter and sum beamformer, we nevertheless happen to be lying within that same lobe, and it's giving a similar sort of response no matter where you are. So what it's saying is that the filter and sum beamformer is not doing a brilliant job, but it's at least spatially robust. It's not going to give you a terrible result like MINT does. And then doing the same with the Oracle and hybrid solutions, we see we've got something in the middle. We end up with a peak at PMOS about 3.8, so this is getting towards the good to excellent range. But we've got a much bigger sweet spot than we ever had with MINT. So what we have effectively done is, by introducing this extra spatial robustness, we've dilated the sweet spot to be bigger than it otherwise would be if we were to use just MINT alone. And in this case, the sweet spot is plus minus 15 centimeters and plus minus 5 centimeters. So what I would imagine is that if you were to have the conference room type scenario and you were to calibrate at some position, at some point in space for where you expect a wanted talker to be, you might calibrate it in a few different positions and then use a source localizer to decide which set of filters to use. And then if the person then moves outside that, then you just fall back to the filter and sum beamformer, which we know is going to be much more robust. So what I've done is established a link between optimal beamforming and channel equalization, and we can view this as a sweet spot dilator for the MINT algorithm. There are several papers that we've written on this. I feel very grateful to Felicia Lim, who had just joined Imperial College just as I was leaving. And I had just come up against this idea of trying to join beamforming and channel equalization together, but never really chased it up. And she started that as a starting point for her PhD, and that got me interested in it again. So I'm very grateful to her for having kicked this off. So this brings me towards the conclusions. So, as I said from the outset, that there is no industry standard dereverberation algorithm. There are beamformers, there are noise suppressors that do some of it, but there's nothing that's really tailor-made for dereverberation. And there are several different techniques that are out there. They're not just channel-based. Some of them are based on spectral subtraction type techniques. Others are based on linear prediction techniques. But I'm concentrating on this problem just because I feel like there should be a solution to this. If we already know a lot about the system that we're trying to invert, we should be able to invert it. And I feel that we're getting a little bit closer. But it remains a very tough problem. There are enhancements that have made it more robust by introducing this idea of channel shortening, and there are other people who have done a lot of work on careful types of regularization. But I feel that with this joint optimization, treating it both simultaneously as a beamforming problem and as a dereverberation problem with channel equalization, that we can somehow get the robustness of a beamformer with the potential dereverberation of a channel equalizer. and I'll leave you with a picture of my cats fighting. My wife took this yesterday, she was very pleased.
Thanks for this wonderful illustrative talk. I think we are having questions. Julius?
Could you just explain again intuitively why the relaxation window helps? How that really, I didn't quite catch how it was improving the robustness.
So when we have a set of inverse filters, they've only got so much of a solution space to play around with. There are only a certain number of degrees of freedom that it has. And if we're very stringent and say we want all taps to be precisely 0 and we want this one tap to be precisely 1, then the solution space for that is fairly small. We can make it larger just by introducing more taps in the equalizer, but it's not practical to keep making them longer and longer. So rather than making the equalizer longer, we say let's not be so stringent about putting zeros exactly here. You can choose whatever solution you like in that solution space, providing everything after the relaxation window has been squashed down, but everything within the relaxation window you can do whatever you like. So it gives you more freedom. And the optimization criteria will when you solve that, it will intrinsically give you the solution that's got the least norm, the smallest norm.
And the relaxation window basically blanks out the early reflections to some extent?
It says don't blank them out, just leave them there.
So they're still there, but they're not constraining, right?
They're not constrained. So they need not necessarily be the early reflection. They can take another form if they like.
Mm-hmm.
There were a couple of papers out of TU Leuven, I think Mark Monen's group. He looked into this problem and said, well, rather than letting them take any value they like, let's force them to be equal to the early taps in channel 1. So that makes it a bit more constrained. But what comes out of it is perceptually nicer, at least from what I've heard, because at least it's a real impulse response. It's not just a whole random set of taps within that relaxation window.
Okay, thank you.
But the thing that really strikes me, and this is something that I should have said earlier, is that by doing this channel shortening, we're trying to squash all those really random taps. I mean, a fairly good reverberator is just a random noise that's got an envelope onto it. And it's those later taps that are going to be the most chaotic, because they're reflections of reflections of reflections. So it's very difficult to predict what those are going to be. So it feels odd that we're trying to squash down the very thing that we can't predict very well when we're doing the estimation. But the things that we do know, the things that are pretty deterministic, like the early reflections that are just going to be wobbling around a little bit, those are the ones that we're saying, let's not squash. And that feels wrong to me. It feels like we're trying to squash the very hardest taps, not the easiest ones.
Well, you're still, I mean, you're estimating either side, because you say you're ignoring a bunch of space solutions you don't care about with the early stuff. So you're not actually modeling it as an exponential, you're still trying to model all the details.
We're still, yeah, exactly. We're modelling the details as much as we possibly can, and it's those details that are totally chaotic. And whether it's because of that chaotic mismatch or whether it's because of noise, I still don't know, but at least I have some idea as to how sensitive it is to the amount of noise and the amount of mismatch that we have. But realistically, that mismatch, a spatial mismatch caused by just a source moving, is pretty bad as far as normalized projection misalignment is concerned.
So your summary graphs, I mean, are great to see it this way, and it's nice to see it, you win in the end. But how robust is it if you just have one more person in the mix and just so one person moves here and moves away a little bit? That's going to change the reflections too. So if you just introduce one additional body to the room.
Oh, what you so you're saying that they're not saying anything; they're just absorbing,
diffracting.
Good question. I mean, the simulations that I was doing were for large rooms using the source image method. If I wanted to simulate a room as big as that with an object that size going up to 8 kilohertz or so, that's quite a difficult thing to simulate with like a GTD with boundary element method.
Could you do it measuring the impulse response?
Oh, you could do it measuring the impulse response, but then you don't know. Is it the presence of the body that changed it, or is it the fact that you're measuring it slightly later on and the temperature's changed slightly, or whatever? I don't know which of it is causing the error. Be nice to do something that would be nice to simulate at least.
Keymark.
Keymark, yeah. Yes.
I remember having come across at least the titles of papers that spoke about reverberation, but they did not use the term channel equalization.
Mm-hmm.
So I can't recall how these methods work, but maybe you want to quickly summarize.
Yeah, well, there's lots of different techniques. There was the reverb challenge was pretty well advertised. It was an IEEE challenge. And I believe the one that won came out of NTT. It was Marc Delcroix and his group. And they used an approach based on linear prediction. So they treated the reverberation as an all-pole system. And if you have an all-pole system, then you can equalize an all-pole system much more easily than you can an all-zero system. But as I recall, and don't quote me on this, they needed a lot of data for it. I think they had an utterance of several minutes, and they used the entire utterance. And the results that they gave were amazing. I couldn't believe how well they worked. But I believe the drawback of that was that it required a huge amount of data.
Yeah, it's not written that way, right?
No, it's not written that way. This at least makes, if we can assume that the impulse response doesn't change significantly in that time, so you do one probing, test it, and then...
Is that realistic?
It's something that, I mean, that was my first set of experiments. I just do a test, measure the impulse responses, then play something back. How realistic that is over time, with furniture moving and temperature changing, that's something that's yet to find out. Yeah.
Can you make it adaptive? Can you do tracking? Dereverberation?
So this, yes, so when I first came across this, it was when I was working in a collaborative European project called Scenic. And the idea of Scenic was that we were trying to look at how reverberation can be used to our advantage. So typically it's seen as a bad thing as far as intelligibility is concerned and as far as automatic speech recognition is concerned. We wanted to know what was good in that, what information could we use. And there was a component of that involved blind system identification. So if you have multiple observations of a source signal, then you can blindly estimate those impulse responses over time. You don't need to have access to the source signal. And the idea was that we would have something that would, over a long period of time, blindly estimate this system and then apply some kind of channel shortening or some kind of channel-based dereverberation approach. Nothing that I ever did indicated that these blindly estimated systems were reliable enough to do that. That doesn't mean it's impossible, it's just when I attempted to do it, trying to do it adaptively, given that we only have the observations, we don't have a closed talking microphone, it's very difficult to do them reliably enough. Another problem that happens with blind system identification is that they don't converge nicely. So if you've got an adaptive supervised system, then you can draw this nice convergence behavior and you get closer and closer and closer. What will happen when you do it blindly is that they will tend to misconverge. And the reason why they misconverge is that a common filter starts appearing in all of the estimated channels. And that's really a downfall of the optimization criterion that is trying to be solved. It turns out that it's not sensitive to channels that have common information. And that's something that, at least as far as an information theoretic problem is concerned, it's something that you're never going to get over. So you never, even though you can get somewhat close when you're doing it blindly, you can never be absolutely sure when to stop adapting. There comes a point where it starts misconverging again. And the rate of risk of misconvergence is to do with the amount of additive noise in the system and mismatches of clocks. And that's another problem. If you're going to try and do this kind of thing live, then you might have a whole load of systems that aren't synchronized, and it's a really tough problem to try to solve. So I feel that if anything like this is going to become practical, I think there's going to have to be some calibration stage. I might be wrong, maybe someone will come up with a blind method of doing it, but the way it stands at the moment, I think that our best shot is to try to have some kind of supervised, semi-supervised system that we've already probed first.
further questions? If there are no more formal questions, I would suggest to thank our speaker again and then meet at Treehouse. For the informal part.
Yes, kindly